Hi, I'm Terry Reid, one of the co-owners of Suzanne Marine, a small startup. The other owner is Fiona Hamilton. The reason I'm making this video, putting it online, is to make people aware of the IP that we've recently patented in the UK. We will be patenting it worldwide as well. This technology we call RSGC, which stands for Recirculating Soignac Gyro Compass. Now, perhaps many of you know what Soignac is, so sorry if I'm boring you by going through it now. The point of the Soignac effect is that the world's rotation, the globe's rotation, means that when you're sending light through a coil, it'll take either a longer or a shorter time to go through the coil than you're expecting, because the light can't go faster than the speed of light, and so the Earth's rotation will affect how long it takes to travel through the coil. That's not a very good explanation, but that's roughly the idea. So RSGC, our invention, relates to this. What's visible in the video now is the demonstrator of the RSGC concept. There's 100 meters of optical fiber in a coil. It's, hopefully you can see that reasonably well. Then the larger of the two PCBs is an Intel Cyclone 5 FPGA developer board. The smaller PCB is what's called an SFP breakout board, where SFP stands for small form factor pluggable, and that is what is used for nearly all installations of fiber Ethernet. They use SFP, with the result that SFP is very cheap for like 10 gigabit Ethernet. It's very cheap. So we were able to put together this demonstrator quite cheaply. And then you'll see there are oscilloscope probes hooked up to stuff there. And the oscilloscope you can see is displaying a step function. And that is the means by which I'm going to demonstrate RSGC to you. What the FPGA board is doing is it's sending a pulse into the coil, and then the function of RSGC is you don't just, with a normal fiber optic gyro, you go through like 6 kilometers of coil, come out the other end and do an interference process to find the change in distance that the signal has gone, compared to a coil traveling through a coil in the opposite direction because of the Earth's rotation. RSGC, the R in RSGC, recirculating, it means we don't do a comparison at the end of a single passage through a 6 kilometer coil. We do a comparison after spending as long as we want to spend recirculating the light through a coil. In this case today, what we're doing is recirculating the light through a 100 meter coil for a second. So it's going through the coil a couple of million times is what that boils down to. Knowing the speed of light in the fiber, it ends up it's going through the coil a couple of million times. Right, on the oscilloscope, the RSGC, sorry, the FPGA board is generating the output pulse and sending that pulse into the SFP, which then sends the pulse as an optical signal through the coil. And a second after it transmitted the initial pulse, the FPGA sends a trigger to the oscilloscope here. And that tells the oscilloscope that exactly a second has passed since the original pulse was sent. And the square wave there is the result of the FPGA using the receive aspect of the SFP and counting the number of times it's sensed the pulse. So it's counted, after it's counted a certain number of times, it gives us that square wave. So after 2 million passes of the pulse through the coil, we get that square wave. And you can see that that's not coincident. That square wave, the edge of that square wave isn't coincident with the with exactly 1 second after the pulse was sent. The T there, that orange T, little orange T, that tells you when the trigger is happening, that the FPGA is sending the trigger. And then you can see the square wave is about, the dotted squares are 250 microseconds at the moment. So the square wave is about 500 and 500 or 600 microseconds after the FPGA said a second has passed. Right. Now the point, so we'll zoom in closer. At the moment we've got 250 microseconds per square there. If we zoom right in so that we've got 10 microseconds per square and then 5 microseconds per square, you can see the square wave is occurring at almost exactly the same time every second. There's a little bit of variation, a microsecond either way. That variation, the change in the time is due to variance due to the FPGA receiving and transmitting the pulse. It's not a big deal because the Sagnac effect at the latitude we're at, I'm near Biggar in Scotland, the Sagnac effect at this latitude is about 6 microseconds. If you are pointing west, which the chair is pointing west at the moment, and then rotate 90 degrees, you'll get either plus or minus 6 microseconds change in the time it takes for the signal to the optical signal to pass through the fiber 2 million times. So at the moment the chair's stationary and we're getting pretty much the pulse occurring at the same time relative to the 1 second mark that the FPGA gives us. But if I rotate the chair, you can see the chair rotating at the same time as we're watching this. There. We got the reception of 2 million iterations through the coil to happen about 20 microseconds earlier than the mean time. Some of that is due to variance in the response due to the FPGA, but a lot of it, that big motion, that big movement of the square, is mostly due to the Soignac effect. You can see we got a good 6 microseconds or more when I rotated the chair back to its original position. I think that gives you a rough idea of how cheap and readily available equipment can be used to demonstrate the Soignac effect. And the key point there is cheap and readily available, because outline designs that I've come up with for low-cost gyro compasses, RSGC is what we're talking about, recirculating Soignac gyro compass. We'd expect that to be fundamentally much cheaper than existing gyro compasses. Less than 1/100th of the price. I won't go into actual pounds, shillings and pence at the moment, but it's that sort of ballpark. It'll be 1/100th of the price of existing fiber optic gyro compasses. And it will be small and light. And it'll be suitable for, in terms of size, power consumption, ability to handle vibration, it'll be suitable for boats, drones, anything that needs to know what its heading is. I think that pretty much covers everything I want to say at the moment. I'll stop there now. Thanks very much.